Good morning. Just like to say thank you for being here so early. Sorry we're running a couple of minutes late. We're going to just take a little of the transition time to make up for that. And without further ado, I'd like to introduce Brandon Phillips to talk to you about etcd version 3. Thank you.
Cool. Thank you, Matthew. So what I'm going to do here today is walk through etcd, give a little bit of introductory background on what etcd is and why we built it, then talk through etcd v3, how it changes, what etcd has been doing since the beginning, how the API changes, how the scaling and performance changes. We'll go through a couple of live demos, hopefully, if the Wi-Fi holds it together. And then at the end, I'll leave about 5 minutes for any questions that you may have. All right, so for some context, who's used etcd before in the room? Okay, fantastic. So let me give you some context on why we built etcd first, just so that we're all on the same page. So the original use case for etcd was for uncoordinated upgrades of the etcd, or of CoreOS clusters. So CoreOS Linux is self-updating, and what that means is that at a given point we have, the idea was that we would have these updates to get pushed to the servers, and it would be very bad if those updates ended up causing a lot of your servers in your cluster to go down at the same time. So you can imagine you have a 6-machine cluster, and then all the updates get applied at the exact same moment because you happen to be unlucky, and then your entire fleet of machines is unavailable. So the original motivation for etcd was to help coordinate these reboots. We called it a reboot lock. And the basic idea was that you would, when a machine was ready to update, you decrement a semaphore automatically, reboot and wait, and then increment that semaphore once the machine came back online. So it looks something like this. The red dot is the semaphore that's being held inside the etcd key value store. This machine would say, I want to reboot, and decrement that semaphore down to 2. So in this configuration, the semaphore is 3, so it means that there's 3 update slots available. And so similarly, the other machines in the cluster may ask for this lock. And then, a 4th machine is ready to do an update. It asks for a lock in the system, but it can't get it. And so the other machines in the cluster are actually applying the update and rebooting and getting onto the new version of CoreOS. And they can race for the lock, but still the lock will continue to operate correctly until such time that the lock is actually released, which there's a typo on the slide that should say 1, and then that machine is able to update. The other use case that etcd started to find itself in is the use case of storing application configuration. So if you have an application, a web application, or some type of backend service running on top of these servers, every time that the application started or restarted, it would go and talk to etcd and get its configuration data. It might be database passwords or load balancer information, or where to find downstream dependent services and what their IP addresses are, or DNS names, etc. So any sort of configuration that you may have passed in through an environment variable or configuration file before is passed in through etcd. And the reason that people like this model and that we found lots of different applications starting to use this is because unlike an environment variable and somewhat unlike a configuration file, you're able to hold a socket open and get pushed updates when configuration changed. Perhaps the downstream load balancer or DNS name you should be using for your database has changed because you had to move and migrate the database somewhere else. A password is being rotated inside the database, a new private key is being used. And so you can push this data using etcd into the application's configuration. Now what would be really bad is if this configuration store that you're relying upon goes down. Because that means that if you reboot any of these individual applications, perhaps the machine that they're running on crashes or something gets rescheduled, you won't be able to get new configuration data. And you won't be able to bring on new nodes that can read that configuration data. So this configuration store needs to remain highly available to your cluster, particularly for reads. And so there's a few requirements that fall out of this use case. One is strong consistency. You want to be able to say that there is a mechanism where only one writer wins when they write into the system. You don't want half the system believing the configuration is one state, say the database password is this, and the other half of the system thinking the database password is that. It doesn't work for these really important configuration pieces of data like locks and et cetera. It needs to be highly available, so it needs to be resistant to individual single points of failures, both through machines or network partitions. And it needs to be watchable. People want updates to be pushed from the key value store into their application. All right, if you're familiar with the CAP theorem, we want to build a CP system, which is consistent and partition tolerant, essentially something like Paxos, if you're familiar with the literature in this particular area of distributed systems. And this is a really common problem, and it's a problem that's been solved in a variety of organizations. So Google essentially relies on this for all of their infrastructure. So the Google file system or Bigtable or Chubby or Spanner all come down to an implementation of Paxos and rely on that implementation for various pieces of configuration data and leader election and sharding keys and these sorts of really important pieces of data. And you see it in other sort of cloud native, like large scale companies. So Amazon has a replicated log that powers EC2. Microsoft has this Boxwood internal product that powers their storage infrastructure. And the Hadoop ecosystem has Zookeeper, which is really the heart of everything in that ecosystem. And so it's a really common problem that there's really only a couple of open source solutions around. And so we built etcd because we felt like there needed to be a solution that took into consideration a lot of the needs of Google's infrastructure for everyone else, Giphy, or what's emerging as cloud native. So as a quick update on etcd, it's pretty popular at this point. Lots of stars on GitHub, which is the most important metric of open source software today. We have about 250 contributors to the project, people who have done both code contributions, filing issues from their production environments, et cetera. And it's used inside of products from Google and Red Hat and EMC and Cisco and Huawei and Baidu and Alibaba and many, many others. So what etcd has sort of become over the last couple of years since it was introduced is the heart of cloud native systems, these distributed systems for running Google-like infrastructure. So you see it inside of things like Kubernetes, the etcd. Etcd is the primary data store of Kubernetes. You see it inside of Cloud Foundry's new Diego, which is the rewrite, well, not a rewrite, but a lot of re-architecture of a lot of Cloud Foundry, networking solutions like Project Calico, and many others. And at its heart, etcd is a fully replicated, highly available, consistent daily store. Now, of course, somebody in the room who's familiar with the literature is going to say, but it's not available, the CAP theorem, blah, blah. What I mean by highly available is that people are able to read from it, and in a lot of cases, availability of reads is important for things that are, doing load balancer configuration or service discovery. All right, so etcd at its heart, key value store, you're able to put keys, get keys, delete keys. You're able to watch keys, so waiting for changes on those keys and updates on those keys. And then you're able to do a compare and swap. So I want to compare and swap the key foo, which is currently at value bar, with bar 1. And I only want to swap it if the current value of that key is bar. And so compare and swap. This is an operation that's really common inside of single systems. It's on an x86 system, there's a single machine instruction that is able to do this. It's a little bit more tricky when you have 5 machines all in a distributed system talking over a network, and at any point, any one of those machines can fail. And that's what etcd does. So the first thing I want to do is walk through a demo of etcd. We have this new thing that we built at play.etcd.io. So what this is a live etcd cluster. We have one other person that's playing around on here, so they may screw up my demo. But this is a live etcd cluster that anybody can walk in, put some keys into it, and then actually kill processes that are in the cluster. So you'll see here that there's five etcd members. The green member is the current leader. And so you can think of etcd as being a small little democracy When the members are all together, they vote on a leader, and that leader is in charge of actually replicating the data to the other members. And so I can do things like put a value into the data store, of course, the ever important foo and bar. And what you'll see is that the hash will update across all these machines. So there's a hash that is hashing the entire store. And so the idea here is that since it's consistent and it's replicated, that as soon as I put it in, all the machines should update to the correct hash. And all of this is slowed down so that humans can read it. This is happening on the order of milliseconds, but for the illustration, we're slowing things down. So the next thing that I'll do here is I'll kill the leader, and that'll send a signal. The signal will deliver to the process, and then it'll get a sig term. And what will happen is that the cluster will actually elect a new leader a few seconds later. Again, this is all slowed down. Generally, this happens on the order of milliseconds. And you can see that a new leader was elected. So I can then tell the cluster, you know what, I want foo to be bar2. You'll see the hash update on the machines that are still alive. And then this machine that was killed earlier, the previous leader, isn't getting any of this data because it's hard down. The process isn't responding. So if we come in here and we restart the process, what will happen is that you'll see it come up, it'll have its old hash value, and then it'll immediately update as the new leader pushes the data that's in the key value store to it. I see that many of you have found the URL. We have 8 users online now. Thank you so much for not killing the leader while I'm doing my demo. You're a very polite crowd. All right. I can't say the same for some of the conferences I've been to. So etcd is designed to survive these single point of failure problems, and it's designed for being very easy to operate. So it allows for runtime reconfiguration, so that 5-member cluster, I can tear one of the members out, I can replace it with a new member. We're adding things like point-in-time backups so that you can say, right now I want to take the snapshot of the entire system and back it up to S3. This is becoming a lot easier with the etcd v3 API that I'll be talking about. And then finally, we have a bunch of extensive metrics designed to help people understand how is etcd working. So this talk is primarily about etcd v3, which is the successor of etcd v2 and the successor of etcd v0. We'll never talk about etcd v1 for a variety of reasons. The main thing was confusion. We immediately had etcd v1 API was deprecated very early on, so we just skipped creating etcd v1 with the v2 API because it was just way too confusing. So the primary thing with etcd is that it has far, far better performance. Way better, more efficient APIs. And it allows for things like getting multiple versions through a long history of keys. So let's say that I have key foo, I'm putting in new versions. I can then go back in time and pick out a particular version of that key. This was sort of possible in etcd v2, but because of the new storage engine and using an MVCC underlying database, we're able to go way back in time on the order of hours or days. We've introduced the idea of transactions, so you can do a transaction across multiple keys, ensure that certain constraints say that this key is at this value, remain true, or these sets of keys are at this value, remain true, in order to update another key. So it's essentially an if-then-else statement in a transaction. We've replaced the concept of TTLs, if you're familiar with that, inside of etcd with the idea of a lease. The difference between a TTL and a lease is that a TTL means that this key is only going to live for, say, 15 seconds, and that's tied to real wall clock time. With a lease, the lease exists for 15 seconds, but if a leader election happens, the lease is renewed. This solves a number of races that we have encountered with people using the etcd TTL API, where they'll have a leader election happen. For a variety of reasons, maybe a partition, the leader election doesn't go forward. Then when the leader election completes, their keys are all expired and they haven't had time to actually update those TTLs. So this essentially means that we put a pause on any writes across leader elections. And then finally, we have a new streaming watch API that's designed for high efficiency. We're actually able to start to do things like cross data center replication, and do snapshotting completely through user space, which means that you're able to get a full view of what's happening in the cluster through a gigantic audit log dump. And it's really efficient for etcd to do this for you. We're also introducing a number of synchronization primitives inside of etcd. So we've introduced barriers, queues, mutexes, priority queues, election, shared transactional memory, read-write mutexes inside of the etcd library, and those will be going into the API over time. We're pretty happy with the etcd v3 API because it allows for implementing these very fundamental distributed concepts using very small amounts of code. This is a line of code comparison between our implementation against the etcd v3 API and the Zookeeper curator implementations of these same data structures and transactional systems. Again, like lines of code is not a perfect comparison, but it does give you a sense of how we're able to implement some of these things really effectively against the API. So comparing etcd v2 and v3, etcd v2 was originally designed for coordination across machines, where you have an order of, say, 10,000 machines that need to be coordinated. So on the order of tens of thousands of keys. etcd v3 is designed for applications in containers to coordinate. So we have on the order of millions of these things that are coordinating with millions of keys. So let's go ahead and look through some comparisons of actual metrics here. So in the case of 1,000 keys, this is a comparison of Zookeeper, Console, and etcd2. So Zookeeper is the most performant database of this type in open source. etcd2 somewhere in the middle between Console and Zookeeper. This is requests per second, write requests per second, 1,000 keys. And what you'll see here is that etcd2, once you get up to a larger number of keys, the snapshots where we actually take the entire data store and write it out to disk, we take these snapshots on a periodic basis, cause etcd to start to fail. So we start to see performance degradation where etcd machines will actually go down to 0 requests per second for a time until that snapshot completes. And in fact, it gets worse. We start to trigger leader elections during these snapshots. And so Zookeeper has pretty good performance here because it has non-blocking full snapshots and pretty efficient memory management for a Java application. Boo. And so by default, Zookeeper is able to keep its requests per second up. But again, once snapshots happen, you can incur these penalties where you get a dip in performance. So this is a case where performance is pretty good, but then for a variety of reasons, a pause because of snapshots triggered an election, and then the snapshot completes and the machine comes back. So we have kind of similar problem patterns. Even though it's less of a problem in Zookeeper, it's still a problem and similar problem to etcd. Now, of course, you can disable snapshots. This isn't really a recommended production setup, but even then you get with Zookeeper these moments where the GC comes in and causes the request per second to crash. So in etcd v3, we're aiming for having really high reliable performance. So we want to have performance similar to Zookeeper's performance with snapshots disabled. And we're able to do this through a new incremental snapshot system inside of etcd v3. And we avoid garbage collection passes and pauses by keeping the storage off heap. So this is etcd v3, and this is a graph that the team is very, very proud of. What this shows is that we have very similar performance. Again, Zookeeper is the most performant open source system of this type. We have very, very similar requests per second throughput with etcd v3, but you notice that the band of requests per second remains really consistent. We stay within about 25% band there. And even better is the latency. So etcd v3, it's a completely flat latency line where because of how the storage engine is designed, we don't incur latency because of these GC pauses. And we're really, really effective at storing keys. So this is 20 million 256 byte keys, about 512 megabytes of data in total. etcd2 required about 10 gigabytes of resident memory to store this 512 megabytes of data. Zookeeper requires about 2.4 gigabytes in our measurements, and etcd v3 requires 0.8. So we have a very nice overhead in keys. And for reliability, let's just talk about it for a second and what's important. So at 99% reliability, if you're designing a system for 99% reliability. In a small system, this is quite easy. Failure is infrequent. Human beings can come in and fix up the 1%. Once you get into large systems with thousands or tens of thousands of machines, it's not okay for a system like etcd that's such a critical piece to be 99% reliable. So we need to design etcd for higher reliability so that human beings don't have to get involved and fix up manually problems that happen. And so at the bottom layer, and etcd is at the very bottom layer of all of these systems, storage systems, load balancer systems, service discovery systems, you need high reliability, and that's what we've designed for. And we achieve reliability through a new write-ahead log system, through snapshots, continuous snapshots, and just tons of punishing functional tests. The write-ahead log inside of etcd is append only. You want the simplest possible thing to persist to disk. And so essentially what happens is every time a change comes into etcd, we append it to the end of this write-ahead log. Simple is really good in these systems that need to persist. And then over the log, we have a rolling CRC checksum that we do over the log. And this is because storage, the underlying disks and OSs can be unreliable in actually getting your bytes to disk, or when the machine recovers from reboot, the bytes that you thought you put to disk may not actually be the bytes that you recover. And in order to achieve improved latency, we have this continuous snapshots system. There's an OSDI paper called Torturing Databases for Fun and Profit, and talks about how on-disk storage systems need to be designed. And there was a system called LMDB that was the winner of this kind of bake-off. And we use a system that's rewritten in Go based on LMDB's similar data structure and ideas called BoltDB, and it's a B+ tree, essentially LMDB rewritten in Go, a little bit simpler. And then the final thing is we test through injection of cluster failures. And we inject a lot of cluster failures all the time. And we do a lot of white box runtime testing. So that hash that you saw in play.etcd.io, we use that similar hash to ensure that the system is in a consistent state. So what we do is that we have this running cluster. We are introducing network partitions. We're killing members of the cluster. We're doing various operations in order to introduce errors. And then we ensure that the cluster remains correct through the use of a client library that's trying to use the cluster while it goes through these failures. So what we have today is a dashboard at dash.etcd.io. And what you'll see here is that the latest version of etcd has ran through 3,402 iterations of this testing. And each of these iterations runs through a variety of different scenarios. Let me go down here. So you can kind of see it. There's different scenarios like ensure that a machine that was down for a long time recovers from an incoming snapshot, recover from incoming snapshot after introducing high latency, etc. And through these iterations, essentially every time we tag a release, we test the software. And through these iterations, we've had 2 failure rounds over what now is about 30,000 different tests. Now, what we've been finding as we progress through etcd v3 is that actually etcd is no longer failing, but our test harness is failing. So there's very high likely that as we investigate this Monday morning on the West Coast in a few hours, this happened over the weekend, these 2 failure rounds, that it's some sort of race or problem in our white box testing. We may have come in too late, or we may have some sort of bug in the harness. Or it could be a legitimate bug in etcd. We've fixed a couple of legitimate bugs over the last week or 2, particularly around unreliable storage and our write-ahead log. All right. And then how etcd achieves this reliability is we use a package called etcd Raft, which is an implementation of the Raft white paper and algorithm state machine. The author of Raft is going to be giving a talk tomorrow about a new project he's been working on. But our package is designed for testing testability and flexibility, and it's used in sort of a number of large-scale database systems today, not just etcd. So you have things like CockroachDB, a database called KV, which has ported it to Rust, I believe, ported our library to Rust, and then a distributed graph database called dgraph. So when comparing etcd to other systems of this type, etcd is really focused on doing one thing and only doing one thing and doing that one thing really, really well. And that's why we don't add a lot of crazy features on top of etcd. You're not going to see etcd with built-in in-process load balancing or DNS or anything like this. It's hard enough to build one of these systems that's reliable, just holding onto this configuration data, not losing it, and keeping really consistent performance. When you have clients that you understand are well-behaved, the moment that you start to throw in every single broken copy of glibc or somebody's resolver that they wrote in their pet language, you start to get into a lot of interesting scenarios that you really don't want to find yourself in. Interesting is bad when building these sorts of systems. You want them to be boring and reliable. All right, so etcd v3 beta is available today. Actually, last week was when we released it. It's designed for high efficiency and scalability, and you can find it at coreos/etcd. As far as future work, we have a number of things that we have in mind. Inside of Google, you'll find that these systems are protected by lots of layers of proxies that do authentication, and they do rate limiting, they do essentially systems to protect the small quorum of 5 to 7 machines that are actually holding on to the important data. We'd like to introduce similar levels of proxying, and there's a lot of interesting work that's going on there. Building for caching, so we want to have cache invalidation, remote cache invalidation APIs between etcd and these proxies. This has been an area of interest, and if anybody works at Google, I'd love to have a chubby 2016 paper, because I understand that there's a lot of interesting cache invalidation that happens between the proxy and the quorum. So if any of you can sneak that out of Google, I'd really appreciate it. Watch coalescing, essentially taking a number of watches from the same client and ensuring that we don't have to duplicate a bunch of data on the wire, and then introducing secondary indexes, which has been of particular interest to things like Kubernetes that are maintaining their own secondary indexes on top of the etcd key value store. With that, I want to also ask that you all get involved. There's a lot of work to do in order to get etcd v3 out the door. A lot of documentation needs to happen. We need more clients using the new v3 API and client bindings. But I'm pretty confident that we'll be getting this release out the door in the next month or so. With that, I want to thank you for your attention. I think I have a few minutes for questions, and thanks again. Yes?
Migration between V2 and V3. Tell me we don't repeat V0 and V2.
Oh, that's a great question. So the question was that between V2 and V3, we don't repeat the same problem that we had between V0 and V2. This problem was that when we started etcd, we didn't know much about designing internal protocols for distributed systems, and versioning is something that's important. And so the protocol, the internal protocol of etcd v0 was tied very closely to the implementation of Raft that we had built. And it was actually a fairly impossible task for us to map it to our new Raft implementation. And so what this meant was that you couldn't smoothly upgrade from etcd v0 to v2, and it was a huge bummer for everyone who had been building on top of etcd. Between etcd v2 and v3, it's fully upgradable from etcd v2.3 to v3. And so you'll just be able to do a rolling upgrade, replace one node with the other, and then once every machine has the v3 API, they'll talk amongst themselves and say, now we can expose the v3 API on our port once it's available to every member. And that's a safety to ensure that you don't end up with 4 out of 5 machines actually understanding v3 and getting very confusing for the clients. So it's a smooth upgrade path from existing v2 clusters to v3 clusters. It's as if any other upgrade inside the v2 series. And then also, we still have the v2 storage engine and API available. So if you want to use that, all of the same APIs that you're used to are there today. But if you want to upgrade to the new API with the new high efficiency storage engine and gRPC engine, you need to use the new API. And primarily, systems like Kubernetes are the ones that need to migrate to this new API, as they've been hitting they've been the ones most stress testing the API and that storage engine. Things like, load balancers that are writing a few dozen keys per second, it's fine for them to use the V2 API moving forward, but Kubernetes is writing tens of thousands or hundreds of thousands of keys, and so they need a more efficient API. Great question, thank you.
When is Kubernetes planning to implement the V3 API?
Great question. So the question was, when is Kubernetes implementing the V3 API? So one of our engineers, Hung Chao, is fixing up the storage engine inside of Kubernetes. By Kubernetes v1.3, which is slated for release in June, that work should be there, and you'll have the option of backing Kubernetes with a v3 cluster. So soon.
Could you talk a bit about the custom efficient memory management that you're doing?
Sure. So the question was, what custom efficient memory management are we doing inside of etcd v3? Really all we've done is we've added the classic thing of you're working in a garbage collecting language and you just ensure that you don't generate garbage. So it's just a lot of memory profiling, ensuring that in the hot path of where keys are written, we recycle objects as much as possible, or we only use the stack instead of putting things on the heap where possible. And there's really no trick except for just lots of grunt work and hard engineering. I wish there was a trick.
Large located chunks that you just custom encoding bits and bytes.
No, so we use BoltDB, which gives us a lot of the snapshotting gains as the primary data store for the keys. And then we just profile the heck out of the hot path of writes and raft replication and all the API objects that are created and destroyed in that hot path. Yep. Cool. Any other questions? Great. Well, if you have any other questions or you'd like to talk about etcd, come grab me at the conference. Otherwise, I hope you enjoy Core OS Fest. Thank you.